Hey everyone, so today I wanted to do a quick video on power series. So just to get started, let's begin with a simple example from something we've seen before, which is a geometric series. So hopefully you should recognize the geometric series as something that looks like some constant x to the power of n, which is going to look like 1 plus x squared on and on forever. And we derive this formula, this equals 1 over 1 minus x. So, kind of an interesting observation as I'm giving you to see is instead of thinking about x as some ratio or r, we can think of x as kind of like a variable in a function. And if we think of the function 1 over 1 minus x, let's say this is equal to f of x, well, these two functions are the same. This long polynomial and this rational function, which in this example doesn't seem very helpful. I mean, if you wanted to calculate like 1 over 1 minus a half, it'd be so much easier to just plug it into the fractions than to add up this infinite sum, which you're not even technically able to do. But we'll find that you can actually find power series for functions that are much more complicated than just this. And it will become helpful there. Now you might remember that the geometric series formula only works when the absolute value of our ratio, or x, is less than 1. That is to say that negative 1 is less than x is less than 1 here. And if you look at our equation, this actually kind of makes sense. I mean, if I plugged in, let's say, 2, I would get 1 plus 2 plus 2 squared plus 2 to the 4th, 2 cubed. And this is obviously going to be growing forever, right? If I plug in 1 even, I get 1 plus 1 plus 1 plus 1, on and on and on. And we can also see that this is going to go in sum to infinity. So clearly, plugging in these numbers won't work. Anything in between, though, works just fine. And that's the power of power series, is that within this bound that we will call the interval of convergence, our function is exactly equal to its power series. There's no difference. And in fact, it might be helpful to think of the function as the power series that it's equal to. Now, to be even more exact, there's also something called the radius of convergence, which in this case just equals 1. It's basically the distance from our centering point that we can go. So, let's formalize this idea a little bit. The idea is that we can ask when a power series converges, because clearly something like 1 over 1 minus 2, or when x equals 2, doesn't equal 1 plus 2 plus 2 squared plus 2 cubed, on and on and on. Clearly these are not the same. This is negative 1, that's infinity. And so the interval and radius of convergence help us answer those questions. So let's kind of generalize the idea of a power series. Since that was just one specific example, a power series is just kind of like a very long or infinitely long polynomial that we write as this kind of scary sum from 0 to infinity of c of n times x minus a to the n. Okay. So let's just figure out what's going on here. For one, we have these factors, x minus a, that are being brought to different powers. This is kind of the polynomial aspect of our equation. And this a is called our center. The point is we can kind of center our polynomial at different points along the function, and doing so will give us slightly different results with slightly different intervals of convergence. But we should note that the center value will not actually change our radius of convergence usually. The coefficients, or c of n, can be thought of like the coefficients of your polynomial. If you have something like x cubed plus 3x squared plus 1. These are kind of the C of n. 1, 3, and 1, right? Coefficients. So, as you might observe, the kind of leading factor to determine if a power series will converge or not is the C of n, because the C of n can vary wildly. So let's just look at a specific example. This might have been one that you've seen before. The sum from 0 to infinity of x to the n over n factorial. So clearly, our C of n here is 1 over n factorial. And we're centered at a equals 0. That's how we'll get this equation. These kind of details are not too important once you get used to power series, but it's interesting to note. So, a natural question is, what might be the radius of convergence? How far can we go from 0 till we hit something that doesn't converge? Well, using our tools from convergence series, let's apply the ratio test, which is going to basically be your best friend when it comes to these power series. And the reason why is that you have this like x to the n, and you'll see what happens when we apply the ratio test. So the ratio test has us take the limit as n goes to infinity of the n plus 1th term, which is x to the n plus 1, over n plus 1 factorial, and divided by the nth term. And that's going to just mean we do this over this. So now you might notice that there's going to be a couple cancellations. I think the clearest one is these x's here. And this is kind of why we usually use the ratio test, because these x's here, we have n plus 1 x's at the top and n x's at the bottom, which means we're just left with 1x. And these kinds of cancellations are super common in these problems. Now, a good thing to remember about limits is that all that really matters is this n that's going to infinity. X has nothing to do with n anymore, right? So let's just move it out. It's basically considered a constant. And finally, note that this n factorial over n plus 1 factorial is just n plus 1. And hopefully you should notice that this limit goes to 0. So in general, we find that this total equation is equal to 0, which, by the ratio test, is less than 1, which means for all x, the power series, let's call this p of x, the power p of x converges. In general, we say that this means r equals infinity. Or you can go infinity to the right of your center port, or infinity to the left. So you can go from negative infinity to infinity. So this is a special example where our power series actually converges everywhere. And you might be able to remember that this is actually equal to e to the x. So this is a much more helpful application of power series. You might have be interested as to how your calculator does certain operations, like how does it know what e to the 1/2 is? Well, it can plug in x equals 1/2 into this power series, calculate a handful of terms, let's say 10, and it'll get it within a pretty decent accuracy of what e, or square root of e, should be. So kind of your calculator in a lot of modern day calculations when it comes to like how spacecrafts work or how engineers build like bridges has to do with these kinds of special functions and plugging them in. So let's go over another example. 1 over 1 minus 2x. And this will introduce another idea when it comes to power series. I want to find the power series of this function. Because right now we're in kind of a rational function form, something we might not like, and I want to turn it into a power series, which is a polynomial, which we do like. Very easy to calculate. You might observe that this is very similar to our f of x equals 1 over 1 minus x. In fact, this is just equal to f of 2x, right? Equals 1 over 1 minus 2x. So we can find these known power series functions and relate them to other series. So once you learn one, you can basically figure out infinitely many functions and find their power series. That's the real tool that comes with learning this topic, is how you're able to extend it to so many other different things. So once we have observed this, let's go back to our equation that f of x is this geometric series. That means f of 2x equals the sum from 0 to infinity of 2x to the n, which can also be written as 2 to the n times x to the n. So now we might ask, what is our radius of convergence? Well, before we use the ratio test, and that would work just fine, since we kind of have it in this nice form, why don't we just use the geometric series test? So the geometric series test will tell us that we need the absolute value of 2x to be less than 1 for this to converge, which means that negative 1 is less than 2x is less than 1, which implies that negative 1/2 is less than x is less than 1/2. So this is our interval of convergence, and our radius of convergence would be 1/2, since we're centered at 0. So for one last example, I'm going to give another kind of non-trivial function. And feel free to pause the video if you want to work on this. I want you to find the power series for this function. So to do this, we're going to observe that this is related to this integral. In fact, it's exactly equal to this integral, right? So, while this is great and all, it doesn't tell us too much unless we decide to use the power series version of 1 over 1 minus x. So keep the integral, don't change anything, but now add this sum. Oh, whoops. X to the n. Okay. Now, luckily, if we write out a couple terms, it's actually pretty easy to take the integral of a polynomial. It's just a bunch of power rules. 1 goes to x goes to x squared over 2, x squared goes to x cubed over 3, and so on and so on. So we get that this is actually just equal to the sum from n equals 0 to infinity of x to the n plus 1 over n plus 1. And don't forget that there is still a plus c. And we'll figure that out in a second. So we should notice that this is actually really interesting. ln, which is something that is kind of weird to calculate. I don't know how I would calculate ln of 1/2. But I could just plug in x equals 1/2 into this equation right here. And plug in a couple terms, I could probably pretty easily approximate what ln of 1/2 should be. So let's quickly figure out what this c value should be. To do this, you might ask, what is a nice value of x to plug into here, this equation? because you can plug in x equals anything into ln, use your calculator and figure it out, but this sum is messy. And I think a nice sum would actually be choosing x equals 0. When we choose x equals 0, this all goes away. And we simply get that negative ln of 1 equals c. But ln of 1 is 0, so we just get c equals 0. Thus, we notice that negative ln of 1 minus x simply equals the sum from 0 to infinity of x to the n plus 1 over n plus 1. And you should check on your own what exactly is the radius of convergence of this. And you should probably find that it should be very similar to the radius of convergence of 1 over 1 minus x. So hopefully you learned a couple tricks. One is what power series are, how you can manipulate them. This is a very important part of learning this topic, is not only learning the important series like 1 over 1 minus x, e to the x, etc., but also learning how to manipulate them, how to plug in 2x, or take the integral of it, or take the derivative of it even. And then finally, how to find the radius of convergence, which is kind of the final important question, right? Because these things don't really matter too much to us if they don't actually work. And they only work within that radius. So the radius is an important question to consider, because if we don't know what it is, there's really no point in trying to even mess with the series at all. Okay, so if you've mastered all three of these things, you've basically mastered power series. Okay, thank you.